Okay, welcome back everyone. Uh, we are going to continue from our last lecture in which we started uh, obtaining the response of a single degree of freedom system subject to harmonic load. Today we are going to focus on damped system. Okay, and then see how the response of a damped single degree of freedom system subject to harmonic load, how does it differ from an undamped system?
Okay, in previous class, we discussed what is the response of a undamped system subject to harmonic excitation. Okay, but we said that in reality or for all practical utility, all the system would have certain amount of damping in them. Okay, so today what we are going to discuss is damped, or maybe I should say viscously damped system. Okay, damped SDOF subject to harmonic excitation. Okay, and as we have been doing till now, what I'm going to do, I'm going to write down my equation of motion for this. So what do I get here as mu dot plus there is a damping term now, cu dot plus stiffness from ku dot, that should be equal to the applied force, which is harmonic in this case, which can be represented as p naught of p naught times sine of omega t. Okay, so now our goal is to obtain the response or solve this differential equation and get the expression for u of t, and then physically interpret all the results that we get from it for different values of the parameter. Okay, now we already know that if we have a linear differential equation, second order differential equation, the total response can be written as sum of particular solution plus complementary solution, where particular solution is any unique solution that satisfies this equation, and complementary solution is the solution to the homogeneous part of this equation by setting the right hand side equal to 0. Okay, now if you look at this carefully, let us first look into the particular solution of this. So what do we basically want is the expression for u p of t. Okay, that should satisfy this equation that I have here. Okay, so let me just write it as sine omega t. Right, now when the system was undamped and this term was not there, we simply said that because the left hand side correspond contain only up and double differential of up, okay, which is equal to some constant times sine omega t, the solution would be in the form of some constant times sine omega t, because if you take sine omega term and then double differentiate it, then it would have some value times again the sine omega term. However, in this case, I have single differentiation of up as well, so I cannot use that solution. In this case, I would have to assume now that my up would be some constant times sine omega t plus another constant times cos of omega t. Okay, and our goal is to find out the values of these constants c and d. All right, so if you take this solution and you substitute in this equation here, okay, basically you would get something like an expression in terms of c and d times sine omega t plus another expression in terms of c and d, and of course zeta m, all those terms would be there. Okay, and then it would be cos omega t, and then I would get this should be equal to p naught of sine omega t. Okay, now this would give me, so as I said, it would be some term plus c plus some terms times d. Similarly here some terms times c plus some terms times d. Okay, so if you compare the coefficient of sine omega t and cos omega t on both sides of the equality, you will get two equations in terms of C and D. And then you can solve it to obtain the expression for C and D. And I would leave that for you to do. Okay, I'm just going to write here the final expression for the value of the constant C and D. Okay, so I can write my C as P naught by K, okay, 1 minus omega by omega n square, and in the denominator I will have this term here plus 2 zeta omega by omega n square. Similarly, the value of t, I can write it as P naught by K, but the numerator is now going to change. I would have this term here, and denominator is going to remain the same what I had for C. So let me just write it here again anyway. Okay. All right, so once you get the values of C and D, you have your particular solution. Now you want your homogeneous solution. Okay, so you want what would be the UC of T that satisfies what equation? Remember, for homogeneous, for complementary solution or homogeneous solution, you need to set the right hand side of the differential equation equal to 0. Okay, so I can write here as C and then okay, and as I have discussed in previous lectures, the solution for this equation would be of the form UC of t would be zeta omega nt, okay, which is to the power exponential power minus zeta omega nt, and then I would have a cos omega d term here, which is the damped frequency, and then I would have sine omega dt. Okay, so the final expression for ut, which is sum of both solution, okay, can be written as sum of up of t and then uc of t. So let me write it this as okay, and then I have the uh, particular solution, which is c sine omega t plus d cos omega t, knowing that c and d have already been evaluated. Okay, so we know the values of constant c and d. What we don't know are the constants a and b, and if the initial conditions are given to you, for example, if u of 0 and velocity u dot of 0, if they are given to you, then you can substitute in this expression here to obtain the constant a and b. All right, now again, like the previous case of an undamped harmonic motion, consider here we have two frequencies now here. I have omega d and then I have omega, which is the forcing or excitation frequency. So the question becomes, at what frequency will the resultant response be, whether it would be at omega d or omega? Now, what I see here, okay, let me just delete this. What I see here is that I have now an exponential term, which is e to the power negative power zeta omega nt, and this term is actually decreasing with time. Okay, I mean this whole term is decreasing with time. So after a certain amount of time, this term would become 0. Okay, and as we said, the term that vibrates at the frequency of the structure, which in this case is omega d, is called the transient solution. Now, the wording or the name transient was not very clear when we were discussing undamped harmonic motion. However, in this case, now you can see why we call it transient solution. If you look at here, after some time, okay, and the time, like, it depends, on the value of what is zeta and omega n, but after some time we know for sure that this term would become almost negligible and equal to 0. So I would be only remaining with this term, the second term here. Okay, so this is called transient solution, okay, or the transient vibration. And the second part, which is the particular solution, it is called steady state. Okay, because steady state is reached, okay, it is a state that is steady after a certain amount of time. Okay, all these vibrations actually died out, and what you are left with is this steady state solution. Okay, so like we did for undamped harmonic motion, let us again try to plot this function. Okay, so now we know that our total vibration consists of two type of vibration. One is the transient response, another one is the steady state response. Transient response is basically damped free vibration, okay, and the steady state is like forced part of the forced vibration at frequency which is equal to the forcing frequency. Okay, so first let me just draw the both responses here. Okay, so if I draw the first part, let us call this u1 and let us call this u2. Okay, so if you try to draw u1 depending upon the initial condition or whatever, it would look like something like damped free vibration. Okay, so it will, the amplitude will keep on decreasing, and after sufficient amount of time it will go to 0. Okay, but then I have also the other part, which is the steady state, and I can see that my steady state is actually, it is not decreasing in amplitude. Okay, it is remaining constant. All right, so let us see it start, let us say at this point, and then it has certain amplitude. Okay, something like that. So this is steady state, and this is transient. Okay, so u1 here and u2 here. So the total response is basically the sum of these two responses. Okay, the total response is actually sum of these two responses. And how I can write, basically draw it, it would look like something like this. Okay, pardon my drawing, I'll try to do as best as I can. So it would look like something like this. Okay, so what is basically happening, I'm summing up these two responses. So initially you can see that the free vibration is about the steady state response. With the time, these vibrations about the steady state vibration actually died out, the transient vibration actually died out, and then the total response, so this is the total response, this is also the total response. Okay, after sufficient amount of time, total response actually converges to a steady state response. Okay, and how fast does it converge? Well, that depends on the value of this term here, right? Because that is what is going to decide that how fast the exponential term is decaying. So how fast is the how fast is the initial response converges to the steady state response, or the total response converges to a steady state response. That depends on the value of damping and the frequency, the natural frequency of the system. Okay, all right, so this is why, so now I hope this definition, why is it called transient and the steady state different part of solution, should be clear to you. Know that the maximum response of a system could still be governed by the during the transient phase. Okay, so as you can see, my steady state is smaller than the total response, and this additional contribution is because of the transient vibration. Okay, however, after certain, like, sufficient amount of time, the total response converges to the steady state response, and that's why for the future discussion we would be focusing on the steady state response. All right, so let us go ahead with our steady state response. Okay, so now we would be focusing on this term here, which is nothing but C sine omega t plus d cos omega t. Okay, but before going to that, we discussed about the concept of resonance in the last lecture, and we said that a resonant frequency is the frequency at which RD, or the deformation response factor, or you can just simply say that resonant frequency is the frequency at which the response becomes maximum. Okay, and the process is actually called the resonant frequency. So for that case, it was when omega was equal to omega d. All right, that was the case when the response was becoming maximum, and it was becoming, so for undamped case, okay, it was getting unbounded, right? Okay, let us see what happens for a damped system. Let us see if we still get a similar kind of behavior. Okay, so what we want to do for omega is equal to omega n, not omega t, for omega equal to omega 1, what I want to do, I would like to find out the expression for ut and then plot it, and then see as the time evolves what happens to the response. Okay, does it become unbounded, okay, or is it unbounded? So we will see. Okay, now let us say for this value of omega by omega n, okay, again let me consider the total solution including the transient solution. What was the total solution that I had written? It was zeta omega nt. I had a cos omega dt plus p sine of omega dt. This was the transient part, and then I had the steady state part, which was c sine omega t plus d cos of omega t. Okay, now I know the expression for c and d, right? So the expression for c is basically nothing but p naught by k. Okay, I have 1 minus omega by omega n square divided by the whole term here. Okay, and then d is also similar to this. However, in the numerator I have minus 2 zeta omega by omega n, and then I have it in the denominator here. Now if I substitute omega by omega n in these two expressions, okay, let us see what do we get. Okay, and so c I would get as, because omega and it is a numerator, this term becomes 0, so c would become 0. D would become, here I get as p naught by k. Okay, so let me write p naught by k as ust naught, which is the peak static displacement. Okay, and then in the numerator I would be left with 2 zeta. In the denominator, remember we had term here, or let me just write here as well so that there is no confusion. Okay, 1 minus omega by omega n square plus 2 zeta omega by omega n square. So when I substitute this, I will get this as 2 zeta whole square. So this I would get, d I would get as ust naught divided by 2 zeta. Okay, now if you substitute these in this expression here, okay, and utilize these initial condition, let us say u0 of 0 and u dot of 0 is equal to 0. So we are assuming that the system was initially at rest. Okay, we can find out the values of a and b. Okay, so after substituting, I'm not going to do all those calculation. Okay, just giving you the values of a and b. Okay, so basically you will get a as ust naught by 2 zeta, and the value of b you would get as ust naught, okay, divided by 2 zeta 1 minus zeta square under root. Okay, so you can substitute these values to the original expression to obtain the value of the expression ut as Let me write it here as UST of naught times 1 by 2 zeta. Okay, and then I have term here cos of omega dt zeta 1 minus 1 zeta square. Okay, and then sine omega dt. This is the transient part of the solution. And then I have another term which is cos omega nt. All right, so I basically get this expression here. Okay, remember that this was the forced vibration, but because omega was equal to omega n, I'm writing it like this. All right, now for a small value of damping, let us say damping is smaller than 10%, or for like it is typically, let us say it is 5%. Okay, I can make some assumption and further simplify this expression here. Okay, so for a small value of damping, small value of damping here. Okay, I can write this expression. I can simplify this expression further. Okay, so my omega d would become omega n. This term I can neglect. Okay, because it becomes very small and multiplied by zeta for a small value of damping. So what I'm going to basically left with my ut as ust naught, okay, divided by 2 zeta, and then here I would have this term here into cos omega nt. Okay, now we have this system. Let us see if we plot this system, how does it look like? Now, can I say that as you increase the value of t, okay, basically this system here would reduce to 0, but overall my ut would never go to 0. Okay, what would happen? Remember that this is a harmonic function cos nt, and this is basically represents the time varying amplitude of this function ut. Okay, so as t increases, this term would vanish, and then I would reach a constant amplitude which would be represented by ust not by 2 zeta, because this term vanish. Of course there's a negative sign, but doesn't matter because cos omega nt is basically vibrating between +1 and -1. Okay, so if I try to plot, let us say here ut divided by ust naught here. Okay, what would basically happen? Let me draw this envelope curve here. Okay, so this represents the asymptotic line, which is the constant amplitude. So in this case, it is 1 by 2 zeta. Remember, 1 by 2 zeta is equal to ut by ust naught. Right, so the amplitude is actually ust naught by 2 zeta, and let us say this is t by tn. So what will happen? The vibration will start like this. Okay, because omega is equal to omega n, the amplitude will start to increase. Okay, however, because the system has some damping, what will happen after some time? Okay, after some time, this term here would vanish, and then due to applied force, I would have a constant amplitude with basically constant amplitude. So a vibration with constant amplitude. So the response does not become unbounded if a system has damping. Instead, the maximum value of ut in this case is actually ust naught by 2 zeta. And as you can see, it is very sensitive to the value of damping. Okay, so if the value of damping is very small, or like let us say bordering to undamped system, let us say 0.01, this ut would be very high, right? But if the value of damping is let us say some reasonable value, let us say 5% or 10%, then my system would still, the response would still be bounded. Now, this is the technique that is typically used in different kind of structural engineering systems. So different structures, let us say, there is always a possibility that due to applied force, and the source of force could be like seismic, wind, or any other type of force that has like different frequencies in them. What happens that if we want to avoid damage to the structure, we include some damping in the structure so that even if there is a resonance, my response is still bounded. Okay, now how do we provide damping in the system? Well, there are various ways to do it. We could, like, people use added damping devices. So you could use supplementary damping using viscous dampers. You can use friction dampers. There are different type of dampers, but the idea is to provide damping in the system because we might not be able to always predict, like what kind of frequency the loading might apply, right? Because loading then would have like different frequencies, and like even if you anticipate that frequencies, this would be the frequencies, it is always to better to take countermeasures, okay, and include damping in the system, because if that there is damping in the system, then the response would always reduce. Okay, so this is one way to actually safeguard, including damping in the structure. Okay, is one of the ways in which we can safeguard our structure against resonance. Okay, I hope this is clear to you. Okay, now what we are going to do here, we have said, we have discussed the basically the resonance phenomena for a damped system. Now I'm going to come back to again my expression for UT. So the total expression, again, let me write it. And I like to write it again and again so that you can have a look at it. Sometimes these expressions could be overwhelming. If you look at them again and again, it would help you to conceptualize each and every term. All right. So let me write it here again. Theta omega nt, I have A cos omega dt plus B sin omega dt, plus then I have the second part of the solution, which is C sin omega t plus t cos omega t. All right, and we said that this response, this transient part of the response, which is vibrating at frequency omega d, is going to die down, okay, after some time. And our main concern here is the steady state response here, and that is what we are going to discuss further. So let us take the steady state response. Okay, so the steady state response is C sin omega t plus d cos omega t. Where's the expression for C and D I have already presented. Okay, now you know that this kind of expression can always be written in the form of u naught, or before writing it as u naught, let me write it like this: c square plus d square. Okay, and I can write this as sin omega t c divided by c square plus d square plus cos omega t t divided by c square plus d square. Okay, so I can write this expression as c square plus t square times sine of omega t, which is the first angle, minus phi. Okay, and what is sine A of minus B? Okay, it is sine A cos B minus cos A sine B. Okay, so if we compare B to phi and then write it here, can I say my tan phi here would be, or just for this, like, let me first write down the first the cos phi. My cos phi is c divided by c square plus d square, and my sin phi is minus of t divided by c square plus t square. All right. Okay. So if I write it further, I can write this thing as u naught times, sorry, not u naught. Let me again write it here as ut of, this is u naught sine of omega t minus phi, where u naught is the dynamic amplitude, okay, which is equal to c square plus d square, okay, and my tan phi here is minus d by c, so I can write phi as tan inverse minus d by c. Okay, now all you need to do is to substitute the values of the expressions d and c. Okay, and then you would be able to find out the value of u naught n. So I know that, let me just write here again, my c is nothing but p naught by k, or I will just write, well, I could either write p naught by k, or I can just write ust of naught, which is the static, my peak static deformation. Okay, so this was this term here, and then I again had the square of the same term in the denominator. Okay, and my d was p naught by k 2 zeta omega by omega n, and then I had the same term that I have in the here. Okay, so when you substitute these expressions, what you would get as u naught as p naught by k times this expression here, which is 1 minus omega by omega n whole square to the power square times 2 zeta omega by omega n square, and this under root. Okay, which I can further write as, remember, p naught by k is nothing but ust of naught times, and this factor, this whole factor here I write as rd. Okay, and if you substitute tan phi, you will get as, okay, 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay, so what we have derived actually, that for a steady state my response can be written as u naught times sine omega t minus phi, which is nothing but ust naught times rd times sine omega t minus phi, where the deformation response factor rd, okay, deformation or displacement response factor, okay, rd is this expression right here. Okay, and phi is called the phase angle, which is nothing but tan inverse again square. Okay, so this basically you need to understand. Okay, so this is the expression for the ut and the expression for deformation response factor and the phase angle. Now let us see what do they mean, right? Now, as we have previously discussed, rd, or from here, rd is basically the ratio of the dynamic amplitude to the static amplitude, and represents the effect of dynamic behavior of the system on the response of the single degree of freedom system. Okay, and phase angle, which is also called phase lag, it represents with respect to the applied force, right? With respect to the applied force, which in this case is Pt, what is the lag that is there in ut? Remember, my pt was nothing but sine of omega t. Okay, however, ut was nothing but some constant times sine of omega t minus phi. So if you try to plot these functions, it would simply mean that sine to omega t starts at 0 depending upon the value of phi. It might start early or it might start late. And this is the difference by which the response would follow the applied force. Okay, so it is something like that. If you apply the force to the right, okay, whether your response is to the left and vice versa. Okay, so with respect to applied force, in which direction is the displacement, phi basically gives you information on that. Okay, so what I have done here, I have considered systems with different values of frequencies ratio. Okay, I consider, let us say, 0.5. Okay, and then I've considered system with omega by omega n is 1 and then 2, and then I've tried to plot the response, the dynamic response ut, and also the static response ust. Okay, not the peak value, remember these are the time variation. Okay, where ust is nothing but whatever your pt is divided by k without the influence of any mass. Okay, and ut is of course the dynamic displacement obtained using solving the differential equation. Okay, so I've tried to obtain for these value, and let us see for these values of frequency ratio, how does the response, the static response, remember static response because it is simply divided, is the force divided by the stiffness, it also represents the force response. Okay, so they are in completely in phase, the static response and the applied force. Okay, so let me, I have done some calculation and got this. Okay, I'll just paste it here for you to see. So what you see here basically, this is the case where omega by omega n was 0.05. This was the case where it was actually 1, and this was the case where it was actually 2. So what do you see? I mean, the blue line is the static one. So my static deformation, or which is also equal to 4, starts at t equal to 0 at 0. However, my dynamic displacement is, when it is 0, it is at some negative value. Okay, and it comes to 0, or let us say this represents the equilibrium position here. Okay, after this much of distance. Okay, so and this is represented by the phase angle. So this here is nothing but phi by 2 pi. Okay, how do I get that? Well, I just substitute the value of u naught sine omega t minus phi, at which it becomes equal to 0. And that gives me the value of time as phi divided by 2 pi. Okay, I hope that is clear to you. Okay, now of course in this case it won't be simply phi divided by 2 pi. You would also have the, sorry, you would also have the term t here, the capital T. Okay, but let us assume if this is represented as t by t, then it would have been phi divided by 2 pi. Okay, similarly here you can see that here it is lagging just a little bit in the same direction. However, if we consider for omega by omega n, we see that when the applied force is 0, okay, the dynamic response is actually the negative minimum, and when it reaches to its maximum value, which is here, the dynamic response is actually 0. So here these responses are lagging by basically 90 degrees. Okay, whatever the response. So here I can say my, remember, my phi was nothing but tan inverse 2 zeta omega by omega n 1 minus omega by omega n square. So when omega by omega 1 is equal to 1, this is actually 90 degrees. Okay, so here the phase difference corresponds to a phase angle of 90 degrees. Okay, now if you do focus at the third one, when omega by omega n starts to increase and becomes a very large value, what you would actually see that if you apply the force to the right, okay, the response would be in the left direction, okay, and vice versa. Okay, and that is evident from here. Okay, when this is reaches the applied displacement or the applied force reaches to its maximum value, my dynamic displacement is in the negative maximum direction. Okay, so I hope you understand what does the phase basically means. Phase is the quantity that is used to show or express the trailing that is there basically between the applied force and the response of the system. All right. Okay. Once that is clear, let us put our focus back on the two expressions which were for RD. Okay. Remember, for RD we obtained as RD equal to 1 minus omega by omega n square square, and then 2 zeta omega by omega n square. All right. And then phi was tan inverse, okay, this expression here. Okay, and what we would like to do, remember the most important parameter here is what? The frequency ratio. So like we did for an undamped system, what we would like to do here is plot this RD, value of RD, and the phase angle for different values of frequencies ratio. Okay, and the question might arise, why do we do that? Why? What is the important, or like, what are the applications? Well, if I know based on the frequency ratio what is the value of RD, and RD represents what? It represents the amplification or reduction in the response due to the dynamic behavior of the structure or due to the frequency ratio here, right? So if I know that, then I could design my system to have a response in within certain level. Okay, within certain, so amplification within a certain level, or reduction within a certain level. Okay, and similarly for the phase. Okay, so let us see how this one looks like. Okay, now if you remember from the previous lecture for an undamped system, okay, and what, maybe let me just draw it in the side. So we had something like this. Okay, all right, so this is, let us say, RD, which is the displacement response factor or deformation response factor, and the horizontal axis was nothing but the frequency ratio. Okay, and just below this we will also draw our phase angle. Okay, so we know that if omega by omega n is very small, for example omega by omega n is less than equal to 1, or let us say close to 0, my RD value actually approaches to 1, right? You can see from this expression, if omega by omega n is equal to 0, then RD becomes 1. Okay, now when omega by omega n becomes very large, like in this case here, what I am seeing here, my RD becomes 0. Okay, so I can say that it starts to increase somewhere here, and then for large value it will converge at some point here. And for undamped system, we saw that the value was actually unbounded at omega by omega n equal to 1. However, if you look at in this case, when omega by omega n equal to 1, my RD is now, it is not infinity anymore, it is not unbounded anymore, it is actually 1 by 2 zeta. You can substitute here. So I would get different expression for RD depending upon the value of zeta. Okay, for a value of, for the undamped system where zeta is 0, this actually becomes unbounded, like something like this. Okay. Okay, and for different value of damping, I would obtain different curves here. Okay, all of them converging to value of 0 at very large value of omega by omega n. So let us say this is a very small value of damping, 0.01. Let us say this is 0.02. This is perhaps 0.05. maybe 0.07, and let us say this is zeta equal to 1. Okay, so as you can see, as you increase the damping in the system, the RD value actually decreases at all frequencies. Okay, and what happens to the phase angle? So let us see here. Okay, phase angle, the expression, remember, let me write that again here, was 2 zeta omega by omega n. Okay, so when zeta equal to very small value, or let us say it's 0, we saw that for undamped case it was, let me first annotate the axes. So this is 0, 90, 180, this is phase angle, this is frequency ratio 0, 1, 2, and 3. So for undamped case, we saw that it was value, for value omega by omega n less than 1, it was 0, and then for greater than 1, it was 180. Okay, now if we have some damping, it would look like something like this. Okay, and as you increase damping, the slope would become more gradual. Okay, so this is the increasing value of damping. Okay. Okay, something like this. So this is increasing value of damping. All right. Okay. So the way we utilize all these results is the design of, like, different type of systems. For example, if somebody says to you, okay, that within the limitation of the properties of a system, you want your response or dynamic amplification, okay, not more than, let us say, if 0, this is, let us say, 1, 2, 3, 4. Okay, whatever here. Okay, they want that, well, the system or the support can sustain only the deformation up to this. Okay, so you would ideally like to design a system for which you can appropriately provide damping so that the response is within this level. Okay, or you can design your system based on the frequency, okay, so that it always falls in this zone. Similarly, if somebody says to you, well, is it possible that I can reduce the response of the system subject to load to less than 1? So the dynamics is actually, a dynamic response is actually smaller than the static. Well, you could say that you are going to design a system, so you're going to provide either omega n, which makes it this value of RD less than equal to 1 here. Okay, so these charts are actually very useful in first understanding the behavior of a dynamic system, and then utilizing it to design different type of systems. Okay, now we saw that our value of RD, or the dynamic response, actually decreases at all values of frequencies if zeta is increased. So RD decreases as zeta is increased. Okay, so my displacement is displacement of the dynamic system. So let me call it dynamic displacement. This decreases with damping for all values of zeta. Okay, so let us see what happens. And, like, this decrease is actually quite sensitive to the value of omega by omega n. For example, if you look at here, if you increase the damping from, let us say, 0.01 here, okay, 0.01 here to 0.05, you don't see much reduction, right? Only this much. However, for the same thing, if you increase the damping at this frequency ratio here, let us say this is 0.8, you can see the reduction is actually this much, which is significant. Okay, so let us now see, depending upon the value of the frequency ratio, how would the RD vary and how would the dynamic response can be characterized. Okay, so let us consider three cases. Okay, in the first case, I would consider I would consider a case where omega by omega n is less than 1. That means that this forcing frequency is very small. Frequency small means what? It is a slowly varying load. Okay, so I can say that it's a slowly varying excitation or force. Now what happens in that case? Okay, if you look at the value of RD and if you substitute omega by omega n equal to 0, as we previously saw, this RD becomes equal to, okay, RD, which is like, U naught UST by U naught. This becomes equal to actually 1, right? So your dynamic displacements actually become equal to the static displacement. Okay, so for a very slowly varying force, your dynamic displacement is actually equal to static displacement, and which is further equal to P naught by K. Okay, and this is actually controlled by the stiffness of the system here. So what I'm basically saying, let us say I had a spring mass damper here. Okay, and if I apply a force and I'm applying the load which is very slowly applied here, like, okay, so what will happen, the effect of mass won't be that much. Okay, and the dynamic displacement would effectively be equal to static displacement. Okay, and it is determined by the stiffness of the system here, and damping does not play a role here, so it is the response is actually not affected by the damping here. All right. Now let us consider the second extreme case, or before going to that, let us consider phi here. What happens to the phase angle? Now, can you imagine if you apply the load very, very slowly here? Okay, your system would move in tandem to the applied load. Okay, so those would be in phase if you apply the load very slowly. So what happens? Phi, even from the expression, when you set omega by omega n equal to 0, phi actually becomes 0. So those are in phase. Okay, and that you can also see from here that if you apply load very slowly, your displacement would move in, or the mass would move in tandem with the applied force. Okay, so those are in these quantities are in phase. Okay, in the second case, I'm considering other extreme situation in which my omega by omega n is great, it's significantly large. So this would be the case when the applied force is varying at a very rapid rate, so we call it a rapidly varying force. Okay, so for a rapidly varying force, okay, if you substitute this value, what you will see, your u naught or your rd basically tends to 0. Okay, and your dynamic displacement is actually 0. All right, and again, I would like to explain you through the same example here. Let us assume this is spring mass, the dynamic system is being represented by this spring mass damper system here. So what I'm basically saying, that if the load is applied at a very, very high frequency, very, very high frequency, the system would not even respond. Okay, so in that case, your dynamic displacement is almost 0. All right. And let us see what happens to the phase of the system. Okay, for a very high value of this one, it becomes, the value becomes 180 degree. All right. And basically, whatever the force that you apply, your mass would actually, whatever small displacement it undergoes, okay, let us say it's a very small displacement, as we said, RD goes to 0, it would effectively be opposite to that applied force. Okay, so ut and pt are completely out of phase. Okay, so if your pt is applied in the right direction, your system would move to the next direction. Of course, we have said that that displacement is very, very small. Okay, but in terms of phase, they would be completely out of phase. All right, now let us consider another case. Okay, when omega by omega n is actually approximately equal to 1. Okay, so basically the forcing frequency is close to the natural frequency of the system, which basically we are trying to discuss about the resonance like situation here. So in this case, what will happen if you look at the value of RD, it becomes 1 by 2 zeta, okay, which is equal to U naught by UST naught. So my peak dynamic displacement U naught is UST naught by 2 zeta. So at frequencies that are very close to the resonant frequencies, okay, your dynamic displacement, okay, it increases, okay, significantly than the static displacement, because remember this typical value of zeta would be around, let us say 5% or 0.05, 0.1, in that sort of order. Okay, so the dynamic displacement is very sensitive to the damping if my applied frequency is close to the natural frequency. Okay, so the response is basically controlled by the damping in the system. All right, and let us see what happens to the phase angle. So phase angle would become, in this case, all right, 90 degree. If you substitute omega by omega n, okay, denominator would be 0, so it would be tan inverse of infinity, which would effectively give you 90 degrees. So basically the applied force PT and UT, they are out of phase by 90 degrees. Okay, so that would mean that when PT achieves its maximum value, UT would reaches to 0, and then when PT goes to negative, again UT reaches to 0. Okay, so it would be something like what we have discussed here, like this situation here. Okay, when it starts at 0, it is minus 90. When it reaches to plus positive amplitude, then it goes to 0. Okay, and when it goes to 0, then basically you have the maximum value of the response. Okay, so those are shifted by 90 degrees. Okay, so these are the typical scenarios. Of course, loading, or it won't be always in these extremes. It would always fall it between, or closer to one of these scenarios. But based on these three, you would be able to interpret or predict somewhat the behavior of the dynamic system. Okay, all right. So basically we'll study that how to obtain the response of a damped single degree of freedom system subject to harmonic excitation. Okay, and then we talked about the physical meaning of different parameters and how it affects the response of the system. All right, so we are going to conclude our lecture here today. All right, thank you.